In this lecture, we will explore mechanical system transfer functions with a 2 degree or more of freedom. We'll use the Laplace transform and use MATLAB for analysis. Key topics include transforming mechanical systems into the Laplace space, writing and solving equations of motions for multi-mass systems, understanding the effects of springs and viscous dampers, and finally using MATLAB to compute and visualize the system response. So table 2.2 has a very useful analysis on how to transform from a component into Laplace space. In other words, to find the impedance. So for a spring system, the impedance simply transforms as K. For a viscous damper, notice the symbol here is an FV for the viscous damper. It transforms as FV times S. And for a mass system, it transforms as M times S squared. This also has a column for the force-velocity relationships and the force displacement relationships. So let's take a look at a 2 degree of freedom system. Here we have two masses, we have three springs, and we have a viscous damper. So the spring have all different spring constants, different masses. Notice also we have friction between the block M1 and the surface and block M2 and the surface. So here the book kind of uses an F for not only the friction force but also for the spring, for the damper friction force. So don't confuse those. Although they're different, they will transform exactly the same under the Laplace transform space. So here's our table. I've sort of shortened it out for this purpose. And so here is the diagram we're given. So notice here, I'm going to go element by element, and I'm going to transform each one of these. So for the spring, they just transforms as their own value. So K1 becomes K1, K2 becomes K2, K3 becomes K3. Now let's look at the the damper. So the damper transforms as FV times S, and so here you see I've replaced the FV sub 3 by FV sub 3S. Similarly for the friction force, it transforms exactly the same. Now for the masses, notice you also have to transform the masses. So M1 becomes M1S squared, M2 becomes M2S squared. So now that we've transformed our mechanical system in the Laplace space, we're going to use the exact same procedure we used for electrical circuits back in the last lecture. We have two masses, so we're going to have two sets of equations. So for M1, the system here, we can simply solve right. All we need to do is find what's inside the brackets. So for the first equation, we'll have some impedances connected to the motion at x1. So we're going to have M1S squared plus, we're going to have FV1S plus FV3S, and we can factor out the S in both terms, plus we'll have K1 and K2. Those are all connected to M1 times, and all that stuff is times x1. So this bracket here is simply this box here. Now this one is minus, so the minus sign is here. Some impedances between x1 and x2. So what is between this block and that block are these two guys. So it's FV3 times S plus K2 times x2. Now equals sum of applied forces at x1. So is there applied force acting on this block? Yes, it's this force here. Now let's move down to the second block. And so here you can see, just like the electric circuits, the first term is going to be exactly the same term as this here, right? Because this value is the same as this value. The only difference is that here we had an x2 and here we'll have an x1. So we can just repeat this value, put it here and put x1. Plus some impedance is connected to the motion at x2. So looking at this value, what is the motion connected to x2? Well, it's M2S squared plus you'll have this friction and you'll have this friction So FV3S plus FV2S, we can factor out the S, plus we'll have K2 and K3. Now, is there any force acting on this block? No. The only external force is this one. So this is equal to 0. So repeating those two equations we had from before, we have two equations and two unknowns. The two unknowns are x1 and x2. So we can find the transfer function. The book wanted us to find g sub s equal x2 over f of s. So here, we have two equations, two unknowns. We can use Cramer's rule, use MATLAB like before to solve this. And what you find is that you get the following value. The delta is this thing here. Yeah, it gets kind of messy, but MATLAB can generate a pretty nice solution for you. That's the beauty of using MATLAB rather than doing this by hand. So book gives us the skill assessment to analyze. So here's another problem. He says, find the transfer function g sub s, which equals x2 over f of s. So here, x2 is the motion of the outside block. M1 is the motion of the inside block. So he gives us the answer. He wants us to find it. So let's go through our analysis, and I'll do this for us. And you can check my handiwork. So here again, we have two blocks, so we're going to have two equations and two unknowns. So here's the table we had before. Again, we have exactly before these. All we need to do is fill in what's inside the blocks here. So we would transform. The first thing to do is transform the circuit, right? Like we did before. So let's analyze block M1. So here, M1 has one spring and three viscous dampers. And it has a mass associated with its motion. And there's one spring between M1 and M2, and there is three viscous dampers between M1 and M2. So here's a viscous damper, here's a viscous damper, and here's a viscous damper. So for the first equation, we have some impedances connected to the motion at x1. So we have m1s squared. Since m1 is 1, it's 1s squared plus 3s plus 1 times x1 minus sum of impedances between x1 and x2. You have the three viscous dampers here, here, and here. So it'd be 3s plus, you got one spring, times x2 equals sum of applied forces. So the force is acting on M1, so this would be F of S. So now let's take a look at block M2. So M2 M2 is this outer box here. So M2 has one spring here. It's got four viscous dampers. So here's a damper, here's a damper, here's a damper, and here's a damper. And it's got a mass associated with its motion. There's one spring between M1 and M2, and there's three viscous dampers between M1 and M2, here, here, and here. So therefore, the equation of motion is going to be given by the following equation. And notice again, the first term is the same as the second term for the block M1 analysis. This one's different. So you're going to have its mass, 1s squared, plus 4s because you've got four viscous dampers, plus 1, that's the spring, equals 0 because there's no external forces acting on block M2. So again, you have two equations, two unknowns. In this case, I'm going to use Cramer's rule to solve for x2, and therefore x2 over f of s, that's our transfer function. Call it g if you want. That's this numerator over this denominator. Okay, so that's it's going to take some practice to get a handle on these mechanical transfer functions. So take a look at the other examples in the book. He works several more examples, and use MATLAB to actually solve for them because the algebra can be kind of messy. Good luck. I'll see you in the next lecture.